A good day to our lecturer. Today, we are going to present our group assignment on engineering economics and project management. Our project title is called EcoVolt Charging Station, which is a sustainable EV charging station program. It uses renewable energy-based EV charging system that utilizes solar energy to charge EV sustainability. And it is located in University Malaya. And here are a few system components that we are using. This is how our system works. First, the solar energy generates electricity through sunlight and directly charged to the EV chargers. Excess energy will be stored in battery for future use. And we also use smart sensors to monitor the battery state of charge, charging duration, and energy consumption. And if the solar energy is insufficient, the system will switch to grid electricity automatically. And here are a few benefits that our project wish to deliver, which are through social, environmental, and economy. And we are going to analyze our proposed solution to an alternative solution on the market. So here are a few project backgrounds. We realize that there's a growing demand of EV charging, but there's lack of renewable energy integration, which makes our energy very expensive and not sustainable. And here are the aims that our project wish to deliver. First, we wish to develop a sustainable charging station, and also we wish to do a smart energy management. And we also wish to apply economic evaluation and project management in our project.
Hello everyone, my name is JUEN, presenting the project plan proposal. The EcoVolt charging station is a localized hybrid clean energy microgrid built for the University Malaya campus. As you can see, our architecture is built on 4 core pillars: a 36 kW peak monocrystalline solar canopy for energy generation, a 60 kWh battery bank for energy storage, 4 commercial grade level 2 AC charging docks for smart delivery, and a dedicated IoT cloud backend to manage telemetry and user billing. Moving to our project scope, geographically, our operations are strictly confined to a designated campus parking segment. Financially, our baseline is bound to an initial capex of 330,000 ringgit, which we evaluate over a strict 5-year operational lifecycle with a 5% MERR. To protect this budget and timeline, we explicitly excluded level 3 DC fast charging, which cleverly avoids the need for expensive substation transformations and disruptive cross-campus trenching. We mapped our deliverables across a 6-phase delivery pathway. We begin with phase 1 and 2, securing site approvals and finalizing our electrical designs. Phases 3 and 4 cover the procurement of our solar logistics and the heavy civil works for the steel canopy foundations. Finally, we move into system integration, wiring, and conclude with rigorous safety load tests before the official handover. To execute this seamlessly, we operate under a matrix organizational structure. Our project leader handles TMB and GPPH license, while our lead electrical and civil specialists manage the physical grid compliance and canopy construction. On the back end, our software operations and financial analysis work in parallel to ensure the station remains technologically integrated, fully safe, and economically viable over its life cycle.
Moving on to the budget and resources section, Alternative A is our baseline grid-only system. It carries a low initial capex of 130,000. However, its annual OPEX is high at 225,000 due to complete reliance on utility grid power. Alternative B is our proposed EcoVolt Smart Hybrid Solar Grid configuration. While this increases the initial capex to 330,000, it optimizes our recurring costs and the OPEX drops to 140,000 because localized solar generation offsets grid consumption. Evaluating the financial metrics side by side reveals the long-term benefits of the hybrid system. An incremental analysis shows that the extra upfront investment of 200,000 yields an incremental annual operating benefit of 85,000. Applying the engineering economy payback formula, this initial premium is fully recovered within 2.35 years. This confirms that the system is financially viable, securing a net life cycle savings of 225,000 for the university over 5 years. Beyond monetary cash flows, our selection accounts for non-monetary engineering criteria. While Alternative A exposes us to tariff inflation and grid disruption, Alternative B delivers structural redundancy and high energy sustainability. Therefore, Alternative B is selected as the optimal engineering solution. It provides a distinct life cycle cost advantage, utilizes strategic battery peak shaving, and fulfills the sustainability mandates of the University Malaya Eco-Campus Blueprint.
This project is a 12-month time-constrained initiative delivering a solar infrastructure and IoT energy management solution. We are operating within a strict master schedule, concluding in the 2026 academic year with a fixed capex budget of 330K. To succeed, we are employing a rigorous resource planning strategy. We are utilizing critical path modeling to manage the dependency, ensuring long-lived hardware is prioritized. We have locked manpower and machinery at a 100% nominal baseline and are using resource modeling on non-critical tasks to protect our budget. We are actively managing physical site constraint, strict regulatory compliance with TNB and Suruhanjaya Tenaga, and the synchronization of civil and software teams. Our execution is structured across 7 phases. We begin with initiation and design, securing JBPH clearance and finalizing single line diagram. We then transition into procurement and civil works for our hardware, including 80 PV panels and 60 kWh battery storage. This led into assembly and software integration, where we deployed our IoT cloud backend, culminating in phase 7 commissioning, which includes EHS safety, audits, and final handover.
So for the social implications, it affects both the quality of life and equity. By reducing the reliance of fossil fuels, we get to reduce greenhouse gases within the campus plaza. Besides that, it helps to boost economic stimulus and also social equity. And to bring this project to life, we have to overcome these 3 challenges, which is ethical, social, and environmental. As for ethical, we have to ensure transparency in energy data and accountability. For social, we have to incorporate student-led committees to maintain and also to provide a multi-language support for inclusivity. And last but not least, environmental, by using sustainable battery chemistry selection to match a 5-year cycle without toxic heavy metals. So here are the alignments with Sustainable Development Goals, SDG. So we get to hit SDG 7, 13, and also SDG 11. And as for campus well-being, we have to boost productivity and improve innovation among the students. And here are the legal compliances, the domain standard or authorities, and also the status as of now. So to conclude, EcoVolt is more than just an infrastructure. It's a transformative blueprint for cultural and environmental change at University Malaya. By combining innovation with ethical responsibility, the project helps to create a financially sound, socially empowering, and also climate positive legacy for the campus and community. Thank you.